The modeling process, proportionality, and geometric similarity. Chapter 2. The modeling process, proportionality, and geometric similarity. Introduction. Reaching conclusions about the behavior of real-world systems. Modeling procedure. 1. Through observation, identify the primary factors involved in real-world behavior, possibly making simplifications. 2. Conjecture tentative relationships among the factors. 3. Apply mathematical analysis to the resultant model. 4. Interpret mathematical conclusions in terms of the real-world problem. 2.1 Mathematical models. Mathematical model. Mathematical construct designed to study a particular real-world system or phenomenon. The nature of the model. Model comparison. Fidelity, the preciseness of a model's representation of reality. Costs, the total cost of the modeling process. Flexibility, the ability to change and control conditions affecting the model as required data are gathered. Construction of models. Step 1. Identify the problem. Example, industry optimization. Step 2. Make assumptions. Reduce the complexity of the problem. Classify the variables. Dependent, independent, some may be neglected. Determine interrelationships among the variables selected for study. Make additional simplifications and consider submodels to hypothesize relationships between variables. Construction of models. Step 3. Solve or interpret the model. Example, solve the resulting mathematical equations or inequalities. Step 4. Verify the model. Does the model answer the problem identified in Step 1? Does it make common sense? Is the model usable in a practical sense? Can we gather the necessary data to operate the model? Test it with real-world data to corroborate the reasonableness of the model. Be careful with extrapolation. Construction of models. Step 5. Implement the model. Put the model in user-friendly mode. Explain the model in terms that the decision makers and users can understand. Step 6. Maintain the model. Remember that the model is derived from a specific problem identified in Step 1 and from the assumptions made in Step 2. Has the original problem changed in any way, or have some previously neglected factors become important? Does one of the submodels need to be adjusted? Iterative nature of model construction. Sensitivity of the model. A model is said to be robust when its conclusions do not depend on the precise satisfaction of the assumptions. A model is fragile if its conclusions do depend on the precise satisfaction of some sort of conditions. The term sensitivity refers to the degree of change in a model's conclusions as some condition on which they depend is varied. The greater the change, the more sensitive is the model to that condition. 2.1 Modeling using proportionality. Recall other examples of proportionality relationships. Transitive rule for proportionality. Geometric interpretation of proportionality. Other examples. Proportionality is a simplifying assumption. The y-intercept must be 0 so that the line passes through the origin. Failure to recognize this point can lead to erroneous results when using our model. Example, volume of water displaced by a boat as it is loaded with cargo. Famous proportionalities. Example, Kepler's third law. Homework, due at the 9th of December 2012, page 31. Problems number 1, 2, 3, 4, 6, 13. Project page 35. Project number 2. Project. Create a model to predict the fuel efficiency of an automobile based on cars already in the market. Page 74. Problems number 3, 5, 6, 8, 10, 12. 2.3 Modeling using geometric similarity. Example. Example, raindrops from a motionless cloud free body diagram. F equals Fg, Ft equals ma. A terminal velocity. Fg, Fd equals 0 or Fg equals Fd. Assume that atmospheric drag on the raindrop is proportional to its surface area s times the square of its speed. Fds v2. Fg equals mg, then Fdm. Assume raindrops are geometrically similar. SL2 and VL3. Therefore SV2/3 and SM2/3, y. From the equation Fg equals Fd we now have MM2/3 VT2. Therefore M1/6 VT, y. Examples: modeling a bass fishing derby. Problem identification. Assumptions. Modeling the size of the terror bird. Modeling fuel efficiency. Problem identification. Note: reschedule class on the 14th of September 2012. 2.4 Automobile gasoline mileage. Scenario. Problem identification. What is the relationship between the speed of a vehicle and its fuel mileage? Assumptions. Automobile gasoline mileage. Restricted problem identification. For a particular driver, driving his or her car on a given day on a level highway at constant highway speeds near the optimal speed for fuel economy, provide a qualitative explanation of how fuel economy varies with small increases in speed. Model formulation and analysis. At constant speed the forces of propulsion and resistance must be in equilibrium. Fp equals Fr. Power available to the car. Creek. Wes represents the amount of fuel burned per unit of time, and K represents the amount of energy per gallon. Automobile gasoline mileage. Power is the product of force and velocity for a constant force. FBV Creek. For constant fuel rating. Fp/V. Resisting force, drag force. FRSV2, and since S is constant FRV2. Since Fp equals Fr/VV2, or SV3. Define gasoline mileage as follows. Mileage equals distance, consumption. Substituting Vt for distance and St for consumption. Mileage equals V/SV2. 2.5 Body weight and height problem identification. For various heights, genders, and age groups, determine upper weight limits that represent maximum levels of acceptability based on physical appearance. Examples. Marathon rule, 2 pounds of body weight per inch of height. Upper weight allowance for acceptance to an armed force.